we're going to talk about Codeforces, round 822 problems, and we're going to deal with problems from A to D. So let's get started. Problem A. It's about selecting 3 sticks, and we have n sticks from A1 up to AN, and we can have any number of operations, which is we select I. It is indices. It is one of the indices. Then we can increase or decrease its length by 1. So it means AI can be AI minus 1 or AI plus 1. And what's the minimum number of operations that you have to perform such that it is possible to select 3 of the n sticks and use them without breaking to form an equilateral triangle. So we have to make equilateral triangle. Equilateral triangle means it has to have the same length for all 3 edges. And we need to find these 3 edges from array A. And also, we have to minimize the number of operations. Then, what I have to do. So, n starts from 3 and up to 300. And AI is less than 10 to 9. So the solution for this is we need to sort first, because we get like randomly permutated numbers, like when n is equal to 8, we get like 3, 1, 4, 1, 5, 9, 2, 6. And the purpose of this problem is about finding same lengths of sticks. We have to find 3 sticks have same length. So to find same length sticks, we need to sort to make it easy. Then it will be 1, 1, 2, 3, 4, 5, 6, 9. Yeah, and because we need only 3 sticks to make equilateral triangle, all we need to do is just iterating from 1 to 8. It's obviously index 1, 2, 3, 4, 5, 6, 7. So at first we just choose these 3, and to make equilateral, we only need 1 operation, which is we need to just decrease this 2 to 1. Then it will be equilateral triangle. Then for this subset, we only need 1 operation, right? And then just need to go through all the way up to n. So it was first trial, when I is equal to 0, and for the second, it's the second one, right? When I is equal to 1, we have 1, 2, 3. And since we have to make all the sticks have same length, this one should be 2, and this one should be 2. The reason that I make them to be 2 is because the middle one should be the one to make the same length for sticks. That's the optimized minimum number of operations to make equilateral triangle. So for this subset, we need 2 operations, which is greater than the before one, and it goes on and on. So it's pretty much everything to solve this problem. We start from first of all we sort in increasing order or descending order, whatever, and then we iterating from 1 to n while choosing 3 indices. And within the 3 indices, we find minimal number of operations. Yeah, that's pretty much everything for problem A. Problem B. Bright, nice, brilliant. And as you can see, there is a pyramid which consists of n floors, floor 1, floor 2, floor 3, floor 4, floor 5, etc. And it looks like a tree because it has parent and children. And also, they are connected by one-way staircases. So every room has 2 staircases, 2 one-way staircases to children. And their floor is different. When floor is defined as I for parent, the children's floor will be floor I plus 1. And in every room, you can either put a torch or leave it empty. Put torch or leave it empty. And there are 3 words that we have to consider. The first one is brightness. Define the brightness of a room, ij, to be the number of rooms with the torch from which you can reach the room I, j through a non-negative number of staircases. So brightness is defined like this. It's staircases. And if T means torch, so torch. And its brightness will be 1, no, 2, because it has 2 torches turned on, and it has 1, and it has 2, 3, 1, because it only have one torch. So it's the definition of brightness. And about nice. The pyramid is called nice if and only if for all floors, all rooms in the floor have the same brightness, which means for the first floor, it has to be like uh, 1, and the second floor it has to be like 1 or 2, and if it is if it is 1, it means that every rooms in the floor 2 has to have brightness as 1, not 2, right? And it works with every floor. And there is brilliance. Define the brilliance of a nice pyramid to be the sum of brightness over the rooms 1, 1, 2, 1, 3, 1, and 1, which means left side of the pyramid, right? Like this. So the purpose of this problem is find an arrangement of torches in the pyramid such that the resulting pyramid is nice and its brilliance is maximized. So we need to maximize brilliance first. No. It have to be the pyramid has to be nice first and maximize brilliance. So how can we solve this problem? Well, since we need to maximize brilliance, I'm gonna put torches in the left side of pyramid first. So the picture of that will be T T T T T. So this way I can make maximized brilliance, right? And then we'll think about nice. So these are staircases among rooms. Lots of them. So it's floor 1, and 1, 1 room has brightness as 1, and 2, 1, 2, 2. 1 has brightness as 2, and it's floor 2. Because all of rooms in the left side is fixed as torch is turned on, we have to make 2,2's brightness as 2. Then I need to put torch in 2,2 because to make brightness as 2. So it is nice. 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 And think about floor 3. 3, 1, 3, 2, 3, 3. The 3, 1 has brightness as 3. So floor 3, floor 1 has to have brightness 1, 2, 3, right? So to make brightness 3 for 3, 2, I have to put torch in room 3,2. Oh no, because we have 2 staircases for every room, so I don't need to put any torch. Then I'll have 3 as brightness, because staircases like this for 3,2. So 3,2 is affected by 2,1, 2,2, and 1,1, and there are 3 keys, which means we have brightness as 3 for 3,2. And we'll think about 3,3. And it's obviously we only have 2 keys, so I need to put T here. Then floor 3 will be nice. And we'll think about floor 4. It's 4,1, 4,2, 4,3, 4,4. And the brightness for 4,1 is 4, right? Yeah. And we'll think about 4,2. Yeah. For 4,2, there are parents like this. And there are 4 T's, so I don't need to put torch here, right? Because there are already 4 T's. And we'll think about 4,3. And 4,3 also have 4 torches, so I don't need to put a torch here. And I need to put torch for room 4,4. And it is nice. And the brightness for every room in the floor is 4. And it's all nice. And brilliance is maximized. So it goes on and on and on. So you can find the rule by doing this. As you can see, all the side numbers are checked as T, right? Left side and right side, they all have torches, and except them, no room has torch, and that's it. We only need to print like 1, 1, 1, 0, 1, 1, 0, 0, 1, goes on and on and on. Yeah, that's the rule for solving this problem B. At first the picture seems pretty hard, but after figuring out how it works, it seems so easy. We only need to print this kind of, you know, for loops. That's it for problem B. Let's start with problem C, removing smallest multiples. So, as you could understand of the description for problem C, we have S and T. And the right example will be this one. For S, it starts from 1 to n. So the n will be 7 here. And for T, we have Actually, we have 1 or 0 for t, but every index of t means 1, 2, 3, 4, something like that. So when ti is equal to 0, which means t does not have number I. So you can make this t to here. So I wrote down x for the number that t does not have. So let me go through the example to understand the problem. So there are numbers from 1 to 7, and t only have 1, 2, 4, 7. And we need to find output, one non-negative integer, the minimum possible total cost of operations such that S would be transformed into T. And the operation is defined like choose a positive integer k, where k is between 1 and n, such that there exists a multiple of k in S. Then delete the smallest multiple of k from S. This operation requires a cost of k. So we can do any number of operation, but every operation have cost of k, and it's necessary to minimize of the cost. So for number 3, it's necessary to find k to erase 3. So k can be 3, right? Yeah, it's the only number for number 3. We can think about like k is equal to 1 and k is equal to 2. When k is equal to 1, then only 1 will be erased, not 3, right? Because the smallest multiple of k will be 1, not 3. So k is equal to 1 will not be the 1 for number 3. And we'll think about k is equal to 2. Because the smallest multiple of 2 will be 2. So that will point these 2, not 3. So it's obvious we can only have 3 for 3. And think about 5. Think about 5. So to erase 5, we can only use 5 as a k. So there will be like k is equal to 1, 2, 3, 4. But divisor for 5 is only 1 and 5. So 2, 3, 4 cannot be the 1. And we can think about when k is equal to 1, but the smallest multiple of 1 will be 1. So this will point out only 1, not the 5. So when k is equal to 1 will not be the right answer for 5. So we only have 5. And next one is 6. The divisor for 6 is 1, 2, 3, 6. So we can think about like this. Since we need to minimize the cost of k, we start from when k is equal to 1. The smallest multiple of 1 will be 1, and since we have 1 in the t, we cannot use it. And the smallest multiple of 2 will be 2, and because we have 2, we cannot use 1. And the smallest multiple of 3 will be 3. And since we don't have 3 in t, we can use this 3 for 6, right? And that's it. So the total cost for this example will be 11 because we chose 3, 5, 3 for case. So we think like to raise x need to use smallest divisor of x, but cannot use 2 for 6, right? Also 1. So here's more example in the problem. So n is equal to 15. So there are 15 numbers, and t only have 1, 2, 5, 6, 7, 10, 12, 13. And we'll think about how to come up with the smallest multiple of k for, for s in a fast way. So for 3, divisor of 3 will be 1 and 3, but because we have 1 in the t, we cannot use 1, so the k will be 3. And divisor for 4 will be 1 to 4. And since we have 1 and 2 in the t, we only can use 4. And the divisor for 8 will be 1, 2, 4, 8. And we have 1 and 2 in the t. And we don't have 4, right? So we can use k as 4. And think about 9. Its divisors are 1, 3, 9. Yep. And we cannot use 1 because we have 1 in the t. And how about 3? It is important to understand. How about 3? Can we use 3? Because we don't have 3 in the t now. Because when we use 3, the multiple of 3 will be like 3, 6, 9, 12, etc. And since we are in the point of 9, we have to think about 3 and 6. So, which means t should not have 3 and 6, but t have 6, right? So we cannot use 3. So left one will be only 9, right? And yeah, it works like this. So I summarized, the operation of how to solve it, how to solving the problem. So if there's SI and the divisors for SI will be A to X, B to Y, C to J, something like that. Or divisors for SI will be 1, A, B, C, D, E, SI. Right? So when we need to erase SI, we need to go through, from 1 to Si, right? To find the smallest multiple of k, because we need to minimize cost of k, which means when the right one is finded, iterating from 1 to si, it's not necessary to go further for b, right? Because b will be greater than a. So in a naive way, it seems to have too many calculations there, so it will end up time limit. So it's not the right way to solve the problem, because as you can see, there are so many things to think about. So about 1, it's a divisor, first divisor for SI, and to erase SI, we need to think about 1 multiple by 1 and 1, 2, 1, 3, etc. And all of these numbers should be 1 to use 1 as a K for SI, right? And it works with A as well. A, 2A, 3A, these numbers should be 0 to use, A as K for SI, and goes on and on and on. That's why it will be end up time limit. So that was naive way to come up with a better solution. And here's the solution. What about checking multiples? Because it took quite a lot to go through every SI, go through divisors of every SI, right? So there will be same number here, right? Something like this. So it's waste of time. So the better solution to optimize the time will be this way. We start with multiple. We only focus on multiple. So I'm gonna make an example here. So n is equal to 15. So S have 15 members, and T have 1, 2, 5, 6, 7, 10, 12, 13. And the pseudocode for this kind of way will be like this. I simply wrote down to understand better before I actually coding something for this problem. So it starts with 1. We pick I from 1 to n. So the I will be 1 at first. So it is I 1, and j will be 1. So ij will be 1 too. So we'll think about ij as an index for t, and because t1, tij is 1, we only break here. so don't need to go further. Then I will be 2, right? I will be 2 and j will be 1. So ij will be 2. Now we think about t2, right? What about t2? Yeah, we have number in t, so we break. Then I will be 3 and j will be 1. So we'll think about t3. Oh, we don't have 3 in the t. So we don't need to break here, and the a and s will be added by 3, which is cost. So here, ij will be cost. Ij will be k. No. I will be k. I means k. So we'll think about 3, 6, 9, etc. until it meets 1, right? Since we don't have 3 in the t, we can go further, like 6, but we have 6 in t, so we break here. And ans is added 3 here. And we'll think about when I is 4. Yeah, it is colored by blue one. And I is k, so 4, 8, 12. We don't have 4 in the t, so 4 will be k here. And what about 8? Yeah, we don't have 8 here too. So we can erase 8 with cost of 4, right? Then what about 12? Yeah, we have 12, so it breaks here. So currently we have 3, 4, 4 as, as for k, cost of k. And when I is equal to 5, we have 5 here, so skip. 6, skip. 7, skip. 8, we have to think about 8 because we don't have it. But the multiple of 8 will be 16, but n is equal to 15, so we don't need to think about, 16. And what about 9? We don't have 9. So the cost of 9 will be 9. And what about 18? We don't have, right? And 10, 11, because it's prime, and 14. It could be deleted by 1 to 7, but it wasn't because there are too many even numbers like 2, 6, 10, and 1 here, and 7 here. So it only left 14. So this is how it works. I mean, how the solution works. And here's the simple pseudocode for solving this problem. Yeah, it was problem C. It was pretty hard to come up with this kind of solution, but we need to focus on how to, end up here, how to be end up here. We start with, understanding the problem first, and to, understand more, we have to think about like naive way first, right? Then, uh, you know, then we can find there are, same numbers checked, and it's unnecessary, right? Because it only consumes the time. So to optimize this kind of, you know, execution, we can think about like multiple ways. Yeah, and it's everything for number C. Number problem D, slime escape. So there are n slimes, and we get K. So we start from Kate slime and right. So there are n slimes, and we start from Kate slime, and each slime has health, and health can be a negative or positive or 0. And uh, we need to find if there's any way to end up being in index 0. Oh, no, no, no. Right. 0 or n plus 1, because we have n slimes and we start from Kate slime and just, find if we can end up in 0 or n plus 1. And there's one more. Every slime has health, and every time I move my slime to another slime, the health will be added. So if my slime has 3 as a health, and the left one has -2, so the time that I move to index 2, my health will be decreased by 2, so it will be 1. Yeah, that's it. I need to find if I can, go to 0 or n plus 1 by not making my slime's health under 0. So every time I move, my health should be greater than or equal to 0. So that's precondition. And here's how to solve this problem. We have to make some indexes as a group. So I start from K, and let's say we're trying to visit 0. So here, right? Here's goal and K minus 1, K plus 1. So well, there's two options, go left or go right. So when we need to go right, because our goal is in the left side, so you know, the easiest way to go to leftmost side is just going, keep going left. But, you know, we need to go to right side. And when? It's obviously we need to go right side when we uh, when we can, obtain more health, right? If it's not, there's no reason to go right side. So in a greedy way, we need to group like this. So there will be like minus line or plus line or minus line, plus line, and total health for this group should be greater than 0, right? If it's not greater than 0, there's no reason to go right side, right? So there will be more groups and their total health will be greater than 0. Yeah, it's the main idea of solving this problem. So k minus 1, k minus 2. So every time we think about right groups first, because we can add more health, and that will make us to go left side more easily, right? So every time we think about right side first, and then go to left side, since it's our uh, way to you know go to goal. Yeah, that's the greedy way to you know go to goal. And the thing is, there could be negative number going through this group, let's say group A and group B. And we need to think about minimum number of group A and B. So minimum number of group A will be like Q, and group B has minimum number as P. The reason that we need to consider minimum number of group A is that our health, our slime's health, always greater or equal to 0, right? Otherwise, it's end of game, right? That's why we need to focus on minimum value for this group. And there will be my health, my current health, and minimum number. And to add group A, I need to think about some of these, and it should be greater or equal to 0. Otherwise, I don't need to go right side, and I cannot. And after adding group A, my health will be rise, and then think about group B, and if the sum of my health and minimum is greater or equal to 0 and something like that, and if not, you know, meeting the requirement, I mean, if the sum of my health and min is less than 0, now is the time to think about left side, because I added every group that I can add. So my health is the best health. Now, you know, left side is easier because there's no group. I just need to observe the left side one. So if k minus 1 slime's health is h, after I visit k minus 1, the total health will be best health plus h. And I need to rethink about the right side and left side and goes on and on. And this is the greedy way to solve this problem. Yeah, and then after finding the solution, when we put goal in the left side, all we need to do is reversing the array, right? And need to find, solution again when, like we have the goal in the left side, because it's all same. Yeah. During finding the solution, we can use greedy and 2 pointers as a technical way. Yeah, that's it for slime escape. Thanks.